Hi everyone, and welcome to our webinar. I'm your host, Tom Pritchard, and I'm joined today by Colin Smith, who will be introducing you to LimitState GEO, which is our geotechnical stability analysis software, and he'll be demoing how it can help you make more of your geotechnical analysis and designs. We're scheduled to run for about 30 minutes in total, and if you have a question at all, then do please feel free to enter it in the webinar interface, and we'll get around to answering as many as we can at the end of the session. So without further ado, I'm going to pass you over to Colin Smith now.
Okay, well, thank you, Tom. Let's just kick off with the next slide. So just to whet your appetite, we'll kick off with a slide showing a selection of the problem types that can be solved by the LimitState GEO software. And as you can see, the software has been designed to identify the critical collapse mechanism for any problem type in the form of a slipline mechanism. So in terms of the specific content of today's webinar, we'll be looking at the types of problem the software can solve, how it works, and the benefits the software can bring the engineer. So to this end, I'll primarily be using the software directly to illustrate the key points, but we'll make use of a few slides at the beginning and end for introduction and summary. And as it's a short presentation, the main aim is to give you a flavor of what the software can do, so there won't be much time to get into the details of all the software functionality. However, there will be time at the end for questions. So we're going to kick off with an introductory example on slope stability. And this is adapted from a real case study. So essentially, we have a slope stability problem involving regrading of the slope for a cutting. Now, we could anticipate that the sort of failure that we'd expect probably going to occur around that steeper portion of the slope. And we might be able to analyze that by hand or by using, for example, a method of slices. However, in this particular problem, there is a potential complexity in that this layer, the thin layer indicated here, is weak, and therefore that would introduce a much more complicated failure mechanism, which is unlikely to be a simple wedge or a circle. So let's see how LimitState GEO analyzes this. So for a short-term analysis, we find the critical mechanism is, as might be anticipated, a local face failure on that very steep portion of the slope. And if we do a long-term analysis, then for the drained case, the critical mechanism we find is a longer sliding mechanism, but both involving that steeper portion. Now, of course, both of those failure modes could have been analyzed by using, for example, the method of slices with a slip circle, and that probably would have given us a pretty good answer. But for more complicated stratifications of soil, the margin of error can increase, and of course there's inherent variability between the different types of method of slices that you might use, for example, Bishop, Morgeston, Price, etc. Now, where LimitState GEO comes into its own is instead of making assumptions, it adopts rigorous plasticity theory that can identify any failure mechanism geometry. And this in particular is needed where the weak layer is modeled. So here, the weak layer, we've highlighted in pale green here. That's a much weaker material. And if we run the analysis, then we get this type of mechanism. So this is a critical mechanism for the short-term undrained case, and that would be pretty hard to model using a slip circle. And there are other non-circular methods available, but they can be a bit hit and miss sometimes. And this particular mechanism is more critical than the previous case, where we didn't model the weak layer. So that was definitely something needed to take into account. Now, I've just illustrated this qualitatively, looking at the mechanisms. Haven't said anything about the quantitative output of the software, but we'll cover that a little later in the presentation. So just to summarize, the sort of challenges we have with traditional analysis methods are that often they require significant assumptions about the failure mechanism, for example, assuming a circular slip surface or a 2 or 3 wedge mechanism. Sometimes there are simplifications made in order to make the analysis tractable. For example, assumed interslice forces in the method of slices. I see there's a misprint there. It says characteristics should say slices. Sometimes for problems that don't fit into the standard type of problem, one might have to adopt hand calculations. That can be slow. And at the other end of the scale, if you're going to move to use finite elements, which of course are very flexible and can handle many geometries, that often requires expert knowledge of the software and the technique, and again, can be somewhat slower. So, looking forward, what do engineers need from their software? Well, we'd say we want software that can reliably identify the critical failure mechanism irrespective of form, software that's simple to understand and use, fast to set up and solve, and gives useful output that's easy to interpret. And we'd argue that LimitState GEO provides all of these. So how does it do that? How does it address those individual cases? So let's first look at the key enabling technology, discontinuity layer optimization. This is used to provide rigorous upper bound plasticity solutions. It's a rapid and direct means of going directly to the collapse state without having to iterate, as you might have to do in an elastoplastic finite element analysis. It's the outcome of a 5-year EPSRC funded research project at the University of Sheffield, and the key method was published in the Proceedings of the Royal Society in 2007. Now, it's actually quite straightforward to explain the core principles of it. So here we have a little domain of soil, rectangular block with a load on it, and supports to the left and the base. What we do is, instead of discretizing this into elements, we populate it with a series of nodes. And then we connect every node to every other node with a potential slip line. And then we use linear optimization to pick out from that very large set of slip lines, where we have 12 nodes. We're going to have 66 possible connections there. Out of that, we use optimization to pick the 6 slip lines that form the critical mechanism using rigorous plasticity theory. And so we get this mechanism on the right, as shown there. And of course, typically we're using thousands of nodes in the analysis, so we're talking millions of potential slip lines. So that gives us a core, robust, reliable, and accurate tool for identifying the critical collapse mechanism, irrespective of the form of the mechanism and the geometry of the overall problem. And just to illustrate that with our previous slope example, if I just run through the solution stage, you can see here all the nodes have been applied to the problem, and the mechanism can be made up of any set of slip lines that form any line joining any pair of nodes. As we scroll through that, what the software does is it trials a few layout of slip lines till it gets to the optimal one, which is mathematically rigorous. And then once it's found the optimal mechanism, it then essentially stitches all those slip lines together to form blocks and can animate it to aid interpretation. As you can see, we've got the animation there. That helps us understand just what is happening in that particular failure mode. So that meets the first of our criteria, and I hope to demonstrate to you the simplicity of use, speed, and ease of interpretation in the last part of the presentation, which we believe will provide the benefits listed here: more accurate results, better designs, better understanding of the problem, time savings, and cost savings. So we're now going to use the software. We'll look at an example of a Gabion wall. So here we have an existing embankment that is to be widened. We're going to use a Gabion wall to help widen that. We're going to backfill that with granular material. And the widened embankment is to take additional loading. So what we want to do is assess the stability of this particular design, and then do a little bit of what-if type questions, just so we get a better feel for what's controlling the design itself. Now, of course, we could analyze this problem using some simple hand calculations. So, for example, we could use a Rankine analysis, but that's slightly complicated because we have those varied surface loads, which make it a little bit more complicated to use a standard formulae, and we have this interface between the fill and the existing embankment. So we're not quite clear how that would affect the Rankine earth pressure distribution. Alternatively, we could do something like a Coulomb wedge analysis using a range of wedge angles. Again, that certainly gets us around the issue of the surface surcharge. But if we're just using a single wedge, we can really only capture one or two failure modes here. That's where the LimitState GEO software, where essentially it can model thousands or millions of wedges, can give you very accurate solutions. So let's see how we can analyze this using LimitState GEO. So what we can do is we can start, for example, with a DXF import of the initial design geometry and then go from there. So that's what we'll do. So just pull across the LimitState GEO window here. So what we have here is a range of buttons on the top on the left-hand side, which perform various functionality, which I'll explain as we go along. And we have a number of windows. Again, I'll explain those as I go along. So for the import, what I'm going to do is import a pre-specified file. So I go import geometry. I'm going to take this Gabion wall study. So we get a little dialog which allows us to modify that import if we wish. I'm just going to skip through that. There is our imported geometry. It has a number of construction lines on it, which will help us if we want to modify that, but I'm just going to turn those off so they don't get in the way. So that's our essential geometry. Now, of course, we need to add materials, properties, boundary conditions, and loading. And potentially, you know, when we're first exploring this type of problem, we might not have a detailed site investigation, but we might want to carry out a scoping study based on a general indication of the soil type. And the software has built-in common materials. So while it may not be fully realistic, I'm just going to add in some simple materials here just for illustrative purposes. So on the left here, we have what's called the Materials Explorer. This has predefined materials, but also we can define our own material properties as well. So what I'm going to do is simply take this very stiff clay, put it on the base there. I'm going to put firm clay everywhere else. Again, this is just for illustrative purposes. And the wall itself, I'm just going to make it a monolithic block of concrete. So I can select all the blocks in one go. And so as well as being able to drag and drop materials onto the area, I can select a number of items and their properties appear in this property editor on the right-hand side of the screen. And I can quickly change the material that it's made of, click concrete here, and then I've got a concrete wall there. I can add loads. If I can click on a boundary here, I'll go back to this select mode. If I click on a boundary here, I can add loads. So here I'm going to add a variable normal load of 10. I have a setting here called adequacy, which basically means we're asking the software how much bigger does that load have to be to cause collapse. We'll come back to that in a moment. So I've got my load, I've got my problem set up, I could run that, and we get a set of diagnostics where the software tries to help you understand the problem that you've presented just for checking, but it's flagged up an error here, no support has been applied, but of course we've forgotten the boundary conditions. So I need to set those. So I'll click on that boundary and I'm going to set that to a fixed boundary. So click on that boundary, set that one to fixed, this boundary to fixed. Again, that one, so that's got all our fixed boundaries. And you'll see that when I click on this, a little window down here, just for help, gives you a brief description of what that particular button or instruction means, so that if you've forgotten, it's there. But it also gives a hyperlink to our user manual if you want more detail. So I've got all the fixed boundaries there. So if I click solve, very quickly the software identifies the critical failure mechanism. So it's a sort of sliding but a bit of a bearing capacity problem. And that's the kind of failure mode that we'd expect. And that's pretty much it. You've solved the problem. You get a numerical quantitative answer here, which is 19.91. What does that mean? Well, if I click on that, a little dialog pops up and it says that variable load we applied at boundary 34. And if I click on that, you can see this is highlighting to show me where it is. We set it, we gave it a characteristic value of 10. We didn't apply any partial factors in this problem, so that gives us a design value of 10. And what it's saying is we have to multiply that by 19.9 in order to get collapse. So that load has to go up to 199, which is pretty big, but then we're doing a short-term undrained analysis here on some relatively strong clay. So in essence, that's how we would build up the problem from scratch. Now, I did that fairly quickly with built-in materials just to save time. What we're going to do is look at the actual problem that was specified, which I've got pre-built here. So this is a problem that we have. And just to check, we can look at some of the material properties. So if I click here, this is our granular fill. On the right-hand side in my property editor, I can look at the properties and see that, yes, it's got the strength 36-degree angle of friction and the unit weight that we'd specified. And I could do the same for the other materials here, the existing fill as an angle of friction of 27 and so on. And the loads, again, this central load was set to 45 from recollection. Variable load, that's 45. So we've set up the properties. And in addition to being able to set properties in bodies of soil, we can also set interface properties. So here, down here, we have an interface material, and that allows us to, for example, where you're not getting full friction on the interface between a solid wall, for example, and the soil, you can modify that, reduce it to 2/3 or a half or whatever is appropriate. Because of time, I'm not going to sort of say more how the Gabion wall has been modeled. It's been modeled so that the blocks can all fail separately. But for this purpose of this presentation, we'll just assume it's going to behave as a monolithic wall, concrete wall, or a Gabion wall, but a monolithic wall. So the other thing we want to do is generally we're going to want to check our designs according to Eurocode. So we can set the partial factors using the built-in scenario manager. So here this has already been set up. We've specified Eurocode 7 design approach 1 combination 2, and we have these factors on unfavorable actions, favorable actions, and material properties. So for example, 1.25 on tan phi. So again, to solve that, find the critical collapse mechanism, I just click the solve button. It finds my failure mechanism. And essentially what I get if I click the animate button is we're getting a sliding failure along the base. And we have an adequacy factor here, a solution of 1.04. And what that means in this context is we've simply defined it as how much bigger do the surface loads that we've applied have to be to cause collapse. So you can see we've got our characteristic values of 10, 45, and 10. Those are factored up by 1.3 in design approach 1 combination 2. And then to get collapse, they have to be factored by a further 1.04 according to the software to get to collapse. Because that number is above 1, we are essentially complying with design approach 1 combination 2. The loads that are applied are insufficient to cause collapse. And we get a sliding failure there. Now, that design as stands passes DA12, so we can be happy with that, but maybe we want to just explore, could we get a bigger margin of safety on that? And if I just solve that again, we can see that part of the failure mechanism actually runs down the interface between the old embankment and the new fill. So that's actually introducing this. So supposing we had decided to excavate that old embankment back a wee bit further, so what I can do is just add a vertex to that point. I can grab that and just drag it away to simulate larger excavation. That should ensure that all the failure occurs in the new stronger fill, and we can see that we've got a slightly higher margin of safety, 1.18. So those surface loads could go higher, but we've still got the same kind of sliding failure. But of course, that means we've got to remove material and put in more fill, so that's not desirable if we can avoid it. One issue is what happens perhaps if someone goes in and excavates the material in front of the wall. So we can drag that down very low and see what that does. Has that got an effect on the solution? And we solve that, and we find the failure mode now changes. That weight of fill actually suppressed a combined sliding failure, and we've got a slight forward rotation of the wall now, and our adequacy factor here has dropped to 0.8, so that means we could only sustain 0.8 of those surface loads. Of course, this whole design is quite sensitive to those. We're only looking at the effect of the surface loads, so these numbers are going to change quite a lot, but it does show that that little bit of fill there does help to give us that extra bit of capacity. So ideally, we need to avoid an excavation. So what else could we do? Well, we could perhaps, under the wall, we could try and put in a stronger material. So I've got this basal deposit, which has a higher strength than the granular fill that we specified. So if I put that in there, just for example, replace that. And then because I've put in a different material there, I need to put a different interface here because we're now interfacing to a new soil underneath the gabions. So I'm going to grab this pre-built, predefined material and just swap it on that base. And run again. And that stronger base fill has suppressed that base failure, and my adequacy factor has gone up above 1. So I could take a little bit more surface load in that case. So hopefully that illustrates how we can use the software. We can ask what-if type questions, get a better feel for the problem, what it's sensitive to, and so on. And it basically gives us a better understanding of the problem. So that completes that demonstration, and we'll just wrap up now with a summary. So hopefully what I've shown you is that in terms of workflow, it's very straightforward from geometry import to reporting. I didn't actually show you the reporting, but the whole problem results can be exported to an RTF file with one click, essentially. Hopefully you've seen how the user is very much in control of the process. You can solve the problem with one click. It's easy to put in partial factors. It's very interactive, so we can ask those what-if type questions to get a better feel for the problem. And we can solve any ULS problem type. We don't have to put in any idealization or correction factors, but we don't need to learn how to use many different programs for slopes, retaining walls, etc. And hopefully, just to expand on that last point, we can solve many ultimate limit state problem types. It's just a list of the types that we can solve and another couple of illustrative mechanisms to complement those we showed at the beginning of the presentation. So that wraps up the presentation. taken slightly longer than I anticipated there, but we've got a few minutes left for questions, so we'll move on to the questions. Okay, so I've got a question about what governs the selection of boundaries. So if I just bring up the software again. I hope I'm answering this correctly, but I'm hoping you're assuming we refer to these boundaries here, the outer boundaries of the problem. So essentially, with this mechanism type of analysis, the main thing is that the mechanism should not intersect the boundary. So here the mechanism is very clear of the boundary, but if the boundary had been placed much closer to the system, sure if I can probably show that by doing something. Put a very soft clay at the base, and a very soft clay here. Let's hope that will work. It comes out as unstable, so there's too much weight there, it would fail, but I was hoping to get a mechanism which went all the way down to the base of the this base boundary. So basically, if the mechanism touches a boundary, it means that that boundary is affecting the analysis. And that would be valid if that boundary was, for example, rigid rock. That's fine, but if we're assuming the soil just continues onwards to the right, the left, and below, then we'd need to pull those boundaries down to account for that. So I hope that answers that question. So if we look at other questions, yeah, so how would we model water? So if I just undo these changes that I just made, and we zoom back in. So water can be modeled in various ways. I have a button here on the left that allows me to draw on a water table, so that's probably the simplest way of doing it. And I could simply draw in a water table that might dive down under the wall like this. In this particular model, it's been set up to be disabled. I'm going to enable it. There we go. So water flowing there. We'll see if that has an effect on the analysis. I think what we find is that it does reduce the capacity a little bit because it's quite low down. And obviously, as we raise that water table up, the capacity will go down more and more as the water table gets higher. Got a question of, can I model seepage? So the software basically allows you to model a simple water table of this nature. If you want to model seepage, the software, you can use the software to import a pre-solved flow net, if you like, or a set of water pressures, a water pressure distribution in your soil domain. And there's a facility to import that, and then the software will then model the scenario with all those pore pressures modeled, so that can represent a more complicated seepage scenario if you wish to do that. Okay, in the interest of keeping you time, because we did say we'll try and keep this to 30 minutes, I'm going to wrap up there. Clearly, if there are any other questions that we haven't answered, we will answer those separately. But I'll pass back to Tom anyway, just to wrap up. So thank you very much for your attention. I hope you found that informative.
Thanks, Colin, and thanks to everybody for joining us today. Just to let you know that we'll make a recording of this available to you over the next couple of days. We'll send out an email so that you can view it on our YouTube channel. And obviously anybody who hasn't been able to make it will also be able to see that. If you follow us on LinkedIn or on Twitter, then you'll get notifications of future sessions that we'll be holding throughout the year. And also LimitState Geo is available to download and try from our website, which is LimitState.com. So again, thanks for everybody for joining us, and we do hope to see you again for one of our future sessions. Goodbye.